Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about projections of the oblique solids. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now the oblique solids are the ones which happen to be inclined to both the reference planes, that is horizontal plane as well as the vertical plane. So let us first of all evaluate the order of inclination of the tetrahedron solid with respect to the two reference planes, that is HP and VP. So a tetrahedron of H 40 millimeter rests on horizontal plane on one of its edges such that the face containing that H is inclined to horizontal plane at an angle of 30 degree, and the edge on which it is resting onto the horizontal plane is further inclined with respect to vertical plane at an angle of 45 degree. So we are required to draw the projections of the solid. So since this tetrahedron solid rests on horizontal plane on one of its edges, and the first inclination of the tetrahedron is with respect to the horizontal plane, that is at an angle of 30 degree. So initially we are going to assume that the top view will provide us with the true shape orientation of the base of this particular tetrahedron, and on the horizontal plane in the top view we are going to obtain this triangular representation of the base over there, and this projection will be drawn below the XY reference line. Now having worked this out, then the next thing is we need to evaluate the appropriate orientation of this tetrahedron with respect to the XY reference line or with respect to the vertical plane. So here you can see that there are two options. We can locate the tetrahedron into this orientation, or we can locate the tetrahedron into this orientation. So if we are going to locate the tetrahedron with respect to VP in this orientation, that is one of the edges of the tetrahedron is parallel to the vertical plane, then you see if we are going to tilt this tetrahedron at an angle of 30 degree to the horizontal plane, so it will be resting either on this corner on HP or it will be resting on this corner on HP. If I tilt it this way, so it will be resting on this corner on the horizontal plane. If I tilt it this way, it will be resting on the horizontal plane on this corner, whereas we are provided with the fact that this tetrahedron is resting on one of its edges onto the horizontal plane. So this case is discarded, that is this orientation is not acceptable. So let us move to the other orientation in which one of the edge of the tetrahedron will be perpendicular to the vertical plane. So if one of the edge of the tetrahedron happens to be perpendicular to the vertical plane, then if we tilt this tetrahedron through this apex in this orientation, in this way, then this tetrahedron will be lying onto the horizontal plane on one of its edges of the base. So this way, this is the correct orientation that we need to follow. And another difference between tetrahedron and any other pyramid we need to understand, in any other pyramid we are provided with the side of the base over there, edge of the base is provided, and the axis height is also provided in any given pyramid over there. But in case of tetrahedron, you see we have been provided with only one information, that is the edge of the base is 40 millimeter, and there is no information regarding the height of this particular tetrahedron. So we will see while we are trying to construct the projections over there that this height of the tetrahedron is not required in case of tetrahedron, whereas the axis height is usually required in case of all other pyramids. So we'll find out why the axis height is not required in the case of the tetrahedron. So we have evaluated that we are going to position this tetrahedron in such a way that one of the base edges of the tetrahedron will be perpendicular to the vertical plane, and this base ABC of the tetrahedron will be available to us. It will be viewed or projected onto the horizontal plane in the top view. So this will be drawn below the XY reference line. So let us draw this tetrahedron. So here you can see tetrahedron is having included angle of 60 degree because this is an equilateral triangle. If you are going to look at it from the top, you are going to view the base of the tetrahedron as an equilateral triangle. So in the equilateral triangle, all the three included angles, they are equal to 60 degree. So from this point, we are going to mark this point as point A, and then this will be point B, and this will be point C. Now, how we have derived at these three slant edges of the tetrahedron? So please check, having marked these points A, B and C over here as the base, which is an equilateral triangle, what we are going to do? From point A, we are going to draw a light line, that is construction line, which will be meeting the BC at its center point, that is perpendicular bisector. Similarly, from end B, once again we will be joining one construction line which will be joining the perpendicular bisector point of AC. Similarly, from C we are going to draw perpendicular bisector of the edge AB of the base. So this way three perpendicular bisectors we are going to draw, and wherever they are going to meet, we are going to get the location of the axis point, that is this point O over here. So with this, once we draw this, you can see point O will be located, and having located point O, now we can join the slant edges over there OA, OB and OC. So this completes our discussion regarding drawing the top view of the tetrahedron, which is having one of its edges perpendicular to the vertical plane. So edge BC of the tetrahedron happens to be perpendicular to the vertical plane. So this is drawn perpendicular to the XY line. So having located this axis point and drawn the slant edges using the object lines, now we have to draw the front view of this. So this is my axis point, location of the axis point. Through this I am going to draw the axis line to work out my front view. Similarly, I am also going to draw the projector through A, and since the base ABC, this is the base ABC, this is perpendicular to the vertical plane, so the projection of point A will be available onto the vertical plane as A dash, because this base happens to rest on the horizontal plane. This point will be A dash, this point will be B dash, and again C dash will be there. So here the projections through B and C will provide me B dash and C dash over here. Now I want to locate point O dash. Now how do I locate point O dash? Because you see no axis height has been provided to me, and I told you earlier that no axis height will be required in the case of tetrahedron, because in this case you can see the edge length is equal to AB equal to 40 millimeter, BC equal to 40 millimeter, CA is also equal to 40 millimeter, and now I need to make use of another edge length of 40 millimeter to complete my front view. And how that edge length will be drawn, please see. We are going to make use of the fundamentals of the rotation of the line. That is, when the apparent length, you can see over here, this is the true length 40 millimeter. This is the true length 40 millimeter. This is also the true length 40 millimeter. This is also the true length, that is OA, OB and OC. They are all true lengths which are 40 millimeter, because this triangle is also equilateral. This triangle is also equilateral, and OBC triangle is also equilateral. So OAB, OAC and OBC, all these triangles, they are also equilateral. That is how we get the construction of the tetrahedron. Now here we have got in the base I have been able to locate the equilateral triangle. Now I will use the fundamentals of the rotation of line. That is, if the apparent length of a line is parallel to the XY line. Please see my edge, slant edge OA. This happens to be parallel to my vertical plane. You just check it out. So this edge BC is perpendicular to the vertical plane. Its projection on vertical plane will be a point view. But this slant edge OA, this happens to be parallel to the vertical plane, and this is projected over here. You can see OA slant edge, it happens to be parallel to the vertical plane. Since it happens to be parallel to the vertical plane, so the projection of edge OA, that is O dash A dash, will be my true length. So what I am going to do, I'll keep the needle of the compass over here, measure this edge length equal to 40 millimeter. So with this as needle point, I'll mark an arc over here such that my distance of the front view, that is O dash A dash, will be the true length of, that is equal to 40 millimeters. So please check, since OA is parallel to XY, this slant edge OA, it is parallel to XY. So the front view of the edge O dash, it is this one, A dash, this will be 40 millimeter. So I know the starting point of this, that is A dash. So from A dash, I'll measure 40 millimeter and make an arc over here, which will be cutting this axis line. So that is why the axis height is not required in the case of the tetrahedron, right? So we are going to mark this as 40 millimeter, and then I'll be marking, please check, A dash is the projection of A onto the vertical plane. B dash and C dash, they are the perpendicular distances, that is projections of points B and C onto the vertical plane, and O dash is my axis point. So I am going to join O dash with B dash C dash. I am going to join O dash with A dash. So this completes my front view, and in this front view again you must remember, please check, projection of O dash C dash, that is OC slant edge, it should be dotted because it is on the back side. Projection of OB should be darker one because it is appearing on the front side. If I am looking from this side, OB will be visible but OC will be hidden. But the projections of OB, they supersede projections of OC because they are overlapping each other. So this hidden line is not drawn. So projection of OB, which are drawn with the help of object line, they will override the dotted line projections of the OC. So OC, you can see it is appearing on the back side, but these projections, that is hidden line, dotted line, will be covered by the projections of slant edge OB over there. That is why you get a dark line. So no hidden line corresponding to O dash C dash is appearing over here because of this overlap. Now the top view has been obtained. The front view of the tetrahedron has also been obtained. Now in the second case, we have been provided that this tetrahedron is resting on the horizontal plane on one of its edges such that the face containing that edge is inclined at an angle of 30 degree to the horizontal plane. So you see, this is the face containing that edge, that is the bottom or the base. So A dash, B dash, C dash, this is the bottom face. So this is inclined at an angle of 30 degree to the horizontal plane. So we need to shift this figure at an angle of 30 degree with rotation should be there through this apex on this side. If I rotate it on this side, it will be resting, my tetrahedron will be resting on the horizontal plane onto this edge. If I rotate it otherwise this way, it will be resting on the corner. So you have to be very, very careful regarding this rotation. So rotation must be followed in this direction. That is, it should be resting on the edge BC, not on the corner A. So now I am going to transfer this triangular figure, that is the front view of elevation, over here such that the base angle means angle of A1 dash, B1 dash and C1 dash surface with respect to HP should be 30 degree. So please see, now I have transferred this. Now once again, rectilinear distances we can use to transfer this. How? Mark this point as point 1. This will be my point 2. This will be my point 3. So onto this projector line of 30 degree, point 1 will be lying on the XY line because it is resting on the ground on the horizontal plane on its edge BC. So BC will be located over here, B1 dash, C1 dash. So point 1 is located here. Measure this distance between point 2. I'll get the second point. From the second point, draw the perpendicular distance, measure this distance over here. So distance of this locus point 2 with O dash. So I am going to mark this point. So this O1 dash will be located. And then go straight and mark point 3. So measure the distance and mark it over here. So using rectilinear distances, we have been able to transfer this front view elevation view in the third view. So third view is always rotation or translation of the previous view, that is the front view elevation. Now having obtained this view, now how many points are there? 1, 2, 3, 4. So these are 4 points which I need to project them downwards. And the projections from the plan projection points will be drawn horizontally. So now we have to work out the corresponding points. So let us work out the corresponding point. This is the corresponding point for the C1. So C1 is lying over here. C1 dash perpendicular below. C, it should be projected horizontally. Similarly, point O is located over here. And then point A is located over here. Point A1 dash projector downward. Point A projector should be drawn horizontally. Similarly, point B. So point, you drop point B projector from here, that is from B1 dash, and then wherever it intersects with the projector of B, so you get point B1, right? So this way this line is projected over here. So once we have located all these 4 points, now we need to work out one very important thing. Which one of these points will be dark? Which one of these points will be dotted one? So please check. Observer is looking at this tetrahedron from the top. So whichever points the observer is able to see will be the top ones over there. But the points which are farthest away from the observer, they are B1 dash and C1 dash. And those points which are closest to the XY reference line, they are also B1 dash and C1 dash. And usually we say that whichever points they are farthest away from the observer and closest to the XY reference line, all points joining them will be drawn dotted. One more condition has to be added, unless those points they are, or unless those edges they are falling in the outer boundary line. So let us first of all join all the lines over here. Now please see, I told you that everything joining B1 dash and C1 dash should be dotted, but I added another condition that unless those edges or those lines they are falling in the boundary. So please check, with respect to C1 this is the boundary, so that is why this is visible, because this is falling in the boundary. Similarly with B1, again O1 B1 is falling in the boundary, so again this particular edge will be dark. Similarly A1 B1 is again falling in the boundary. So since the edge A1 B1 is falling in the boundary, so again this has to be drawn dark. Similarly the final edge C1 A1, this is also falling in the boundary. So since these 4 edges, even though they are originating from B1 and C1, but they are part of the boundary of the object, so any edge which is going to give you the boundary of the object can never be dotted. So only if one edge is left out, which is this B1 C1, which is quite obvious. You see, this is my B1 C1. If I rotate it in this direction, so only this edge, this will be covered with the help of this slant edge, and this surface over there. That is these two surfaces, this surface OAC and OAB. These two surfaces will be covering this particular portion. But still, even if you turn it, still this will be part of the boundary. Still this will be part of the boundary. So this is also boundary. This is also boundary. So that is why OB and OC will be dark. Just see, O1 B1 and O1 C1 will be boundary. And similarly, even if you tilt this, this portion is still the boundary. This portion is still the boundary. So anything which defines the boundary cannot be dotted. So even if you tilt it, only this line, this edge of the base, so this will be covered by this surface and this surface over there. So that is why there is only one dotted line in this figure, right? So we have discussed one thing, that even though that the points B1 dash and C1 dash, they used to be farthest away, located farthest away from the observer, but they are giving us four edges which are part of the boundary of the object. So that is why these edges will be drawn dark, whereas only one edge on which it was resting, so this edge will be overshadowed by these two surfaces over there. Now further you note that there is another slant edge which is visible, that is O1A1. So please check this out. This is another slant edge which is OA. So once we have rotated this, so this edge will be the intersection of the face OAC and OAB. So these two faces, they are going to intersect at the edge OA. So O1 A1 also needs to be joined. So here we have joined the edge O1 A1. So now we will verify. So we have to join the edges A, B, C of the base. So please see, we have joined A1, B1 and C1. Similarly, we have joined OA, OB and OC. So please check, O1 A1 has been joined, O1 B1 has been joined and O1 C1 has been joined. So this completes our plan projection when the tetrahedron is resting onto the ground with on one of the edges, and the face containing that edge is inclined at an angle of 30 degree. Now you see this edge, that is BC. So we have tilted this tetrahedron towards this side so that this face ABC is inclined at an angle of 30 degree, and this edge BC is still parallel to the horizontal plane. So this edge BC is still, since it is contained by HP, so we can see that B1 C1. So even though this is dotted, this is overshadowed by these two surfaces, but still this edge BC is the true length. So now in the next stage it is provided to us that the edge on which this tetrahedron rests on the horizontal plane, that is B1 dash C1 dash, it is further inclined with respect to the vertical plane at an angle of 45 degree. So we have to now rotate or translate this plan projection over here at an angle of 45 such that this edge B1 C1, which happens to be true length, will be inclined with respect to VP at an angle of 45 degree. So this angle of 45 degree, which corresponds to the inclination of the true length of the edge B1 C1, will be called as angle phi. So please see, angle phi is the angle of inclination of the true length with respect to VP. That is why we have called this angle as angle phi. Now you see, we have drawn a projection line at an angle of 45 degree. Now this figure, that is the top view figure, will be transferred over here in step 5 such that B1 C1 will be located along this particular line. So this is the true length which will be located over here. So just see, we have transferred this. Now let us see once again how rectilinear distances will be used to transfer this particular figure. I will mark this point as point number 1. This point will be my point number 2. This point will be my point number 3. So points 1, 2 and 3, the distances will be measured, and these points 3.1, point 2 and point 3 will be marked over here. So from point 1 and 3, automatically C2 and B2 will be located because there is zero vertical distance over here. From point 2, you go this much distance downwards. This will give you the location of O2, and you go in the other direction by from this location to this location, measure the distance. So from this locus line, measure the distance of A1. You are going to get the location of the point A2. So having located all these 4 points over here, Now we have to join all these 4 points in the same manner as they were done in the previous plan projection view. That is, whichever lines were dark, they will be drawn dark over there. Whichever lines were hidden one, that is dotted ones. So same line we have drawn over here as dotted one. So this is the top view of an oblique lamina which is inclined with both the reference planes. Now we have to now draw the view number 6, which is going to be the front view. So in order to draw view 6, the vertical projectors from all these 4 points, they need to be drawn, and horizontal projectors through these 4 points, they will be drawn. So and the corresponding points will be worked out. So let us work out the corresponding points. Now here you can see this is the corresponding point for C2 dash. The vertical projector from C2 and the horizontal projector from C1 dash, wherever both of them intersect, you get the point C2 dash. Similarly, vertical projector through B2 and the horizontal projector through B1 dash, wherever they intersect, the point B2 dash will be located. Similarly, vertical projector through A2 and the horizontal projector through the A1 dash will give us the point A2 dash. And finally, fourth point, vertical projector through the O2 and the horizontal projector through the O1 dash, they will give us the point O2 dash. Now again, same thing we have to follow. We have to join A2 dash, B2 dash, C2 dash. We have also to join O2 dash, A2 dash, O2 dash, C2 dash and O2 dash, B2 dash. But we need to work out which edges will be dark and which edges will be dotted. So since you see we are looking from this side, the observer is looking at this tetrahedron from this side. The farthest point from the observer and the closest to the plane XY, reference line XY, is C2. So any lines which are going to be joined with C2 dash, they will be dotted unless, once again, there is binding condition, unless those edges or those lines, they will be falling onto the boundary. If any edge is falling onto the boundary, that will be drawn dark. But any other edge which is not coming under the boundary and it is containing corner C2 dash, so that particular edge will be drawn dotted. So let us start joining the points. So please see, as I have told you, we are going to join A2 dash, B2 dash and C2 dash. So this is first thing. Second, O2 dash, B2 dash, O2 dash, A2 dash and O2 dash, C2 dash has been joined. So please see, there are 3 edges which contain corner C2 dash. That is, one is O2 dash, C2 dash, which is not contained by the boundary. So that is why this edge has been drawn as dotted one. Whereas the edge B2 dash, C2 dash, since it defines the boundary of the tetrahedron, so any edge which defines the boundary cannot be dotted. Similarly over here, edge A2 dash, C2 dash is again defining the boundary of the tetrahedron. So that is why this edge is again drawn by the object line or the darker line. Whereas there is no question about darkening of these 3 edges over here, because they are not passing through C2 dash. So all of these 3 edges, they will be drawn darker one. So again I repeat, since the observer is looking from this side, any edge which is joined by C2, that is C2 dash, has to be drawn dotted. But since these 2 edges, they are contained by the boundary, so they are not drawn dotted, so they have been drawn darker ones. Whereas this is the edge which is not joined by the boundary, which is not contained by the boundary. So that is why, since it is falling within the surface of the object, so that is why O2 dash, C2 dash has been drawn dotted. So with this, we complete the discussion regarding the projections of an oblique tetrahedron solid which is inclined with respect to both the reference planes, that is horizontal plane and the vertical plane. So we'll continue with further discussion on some more oblique solids in the next lectures. So thank you very much. Thanks a lot. Thank you.